Welcome to Modeling Using Variation. You remember having learned about direct variation and inverse variation, which can be written in a different way, but this one's more common. And a joint variation is simply a direct variation that has two variables over here. You have two variables, not just one. In a combined variation, you have both a direct variation and an inverse variation. And it also can be written with a joint. So it could be y equals k x, call it w, over z. So you could be multiplying twice up there and down the bottom have an inverse. You could have two on the bottom. There's numerous ways that you could do it as long as you call the ones on top direct or joint, and underneath it's inverse. Well, that said, let's actually apply these to a couple of application problems. The gravitational force with which Earth attracts an object varies inversely. Ooh, I got a nice telling us which one we're going to use. With the square of the distance from the center of Earth. In fact, this first line gives us the formula we're going to use. The second line, a gravitational force of 0.4 pounds acts on an object 8,000 miles from the Earth's center. Pounds, I'll put there. What happens here? No, I guess if it's 0.4 pound, it's less than 1, so I actually don't put the S with it. Just being careful of English grammar, making sure we have that correct too. So what that does is that gives us a couple of starting numbers that help us to find the K that's in every one of those direct or other type of all of those variation equations. Find the force of attraction on an object that's 6,000 miles from the center of the Earth. So that's the goal that we're going to have, but we have to make the formula correct first. So I like to use X and Y. However, this one lends itself, more than lends itself, we should think of it in terms of F of the force. And then over here, we have a distance. So with distance, we can use D. So those are the two variables that we'll use. But also, let's think about the fact that the distance would count as the X value because it's the independent variable. Okay, X, D, whatever we call it, the independent variable is the one that goes here in any of these equations. And that's because both of these, that's because the Y value that's the independent. So I'm going to call independent. I may have said it wrong before, so let me make sure I correct it now. The independent variable is the one you choose to put in, and you can put any number in, but it causes the result that gives you the dependent variable. So the Y depends upon whatever you put in for X. In every one of these cases, the Y depends upon the X here, the Y depends upon the X here, the Y depends upon the X here, and the Z, X and Z, or X and W over here. So you need those in order to get the Y. All right, so that means that for an inverse, we're going to have the function equals K over D. That's because Y equals KX. And since that's going to be D and that's going to be F, we're going to write it with D and F. Okay. However, it's the square of the distance, so we have to put D squared. So that makes this a little bit different, but it's still the same concept, really. The second one now tells us we have a force of 0.4, and that's equal to K over the distance, 8,000, which has to be squared. So that means that K is equal to 8,000 squared times 0.4. Do that in the calculator, and you get 25,600,000. Okay. That gives us enough now to give us that the force equals 25,600,000 to be precise here, divided by the distance squared. Now we have something that works. We needed to find the K, we have done it. And then the part that we're trying to find is when it's 6,000. So we're trying to find the force of attraction when the distance is 6,000 and then it's 6,000 squared. 6,000 being squared. Sure, that's really a zero there. And then 25,600,000. Well, this number becomes 36 million when you square it. So we have 25.6 million divided by 36 million, and the force comes to approximately 0.71. Come back up here to see what kind of units it was. Okay, so it's pounds, 0.4 of a pound, and this is 0.7 pound. Okay, and that tells us what our force is. It's approximately, so we round it, but 2 decimal places, unless you know different, then that's appropriate for most situations, unless you're using really large 3-digit numbers and larger. Okay, let's take a look now at a different application problem. This one still has the same kind of concept. We're going to find the formula for it through part of what it tells us. And that's what this part is. That will tell us the formula. Then we're going to find some information to help us find the K. So this part will get us the K. We have 2 masses separated by 1 meter exerting a force of attraction of this amount when I use newtons for the unit of measure. So let's take this and figure out what that will be. So force of attraction varies jointly between 2 bodies, varies jointly. That means we're going to have 2 numbers multiplying on top. So here are the 2 numbers, the product of their masses, the 2 bodies' masses. In fact, we'll call one of them mass 1 and the other one mass 2. And so those are going to multiply times the K. So we're going to have K times M sub 1 and M sub 2. So the first body's mass and second body's mass. And then inversely, notice that we have a second one here. Inversely, as the square of the distance between them. Well, we just already found D being squared. We did that in the last one, so we're going to count that. So we're just really adding in a joint part where it's the masses of the 2 bodies that will multiply also times the K. So this is the basic formula here. Now we need to find out what the K is. So let's take a look at the fact that 1 kilogram masses gives us M1 and M2 because they're both 1 kilograms each. And they're separated by 1 meter, so that's the distance. So let's actually put those in and get that. Force is equal to 6.67 times 10 to the negative 11th newtons times 1 kilogram times 1 kilogram divided by the distance of 1 meter being squared. Okay, so it's like kilograms times meters, except that it's going to be in newtons that we want to force it. That's what kilograms over meters will give us. That's just 1. So 1 times 1 is 1, so the top is this number, and 1 squared is 1, so it's just that number over 1, which means the K is equal to just that number, 6.67 times 10 to the negative 11. Now, why do we do that? So we can make this formula a function, or rather the force. The force is equal to 6.67 times 10 to the negative 11 times M1 times M2. The mass of the first one, the mass of the second, divided by the distance between them. Well, then, now we have to look at the rest of this. What's the gravitational force exerted by Earth on a satellite, 1,000 kilogram satellites, orbiting an altitude of, this is a typo. Please change it to 300 kilometers. We know that because down here it says that we're adding 300 to the Earth's radius. So it's an altitude of 300 kilometers. Here's the Earth. Here's an asteroid going around it. Well, no, a satellite. It's a satellite going around it. Better not be an asteroid unless it doesn't hit it. So this distance is 300 kilometers. This distance, the radius, is 6,400. So we add them together to get 6,700. So this will be 6,700. The mass of the satellite, come back to it, the mass of the satellite was 1,000 there. And the mass of Earth tells us is this amount, 5 point, and so on. So let's actually now write that. Force is equal to 6.67 times 10 to the negative 11th times 1,000 times 5.98 times 10 to the 24th power. This is the same as 10 to the third power. On the bottom, it's 6,700 and 6,700 squared. Okay? So I'll write that first here, 6,700 squared. Now, let's put all those together. Okay? So we're going to multiply, force is equal to, let's come over here, and it's 6.67 times 5.98. We have to multiply these parts that don't go with the times 10. And then we have to add all the exponents, 10 to the negative 11th, and we have a 10 to the third, and we have a 5.98 times 10 to the 24th. So here, this comes to approximately 40 times, and then let's add these all up. That's 27, take away 11. That's 10 to the 16th power. 27, yep, 16th power. But then there's one decimal here that has to move over. So if it's moving over like that, then we have to add 1 to this 16. So it's actually 4.0. That's 4.0. Yep, times 10 to the 17th. So we put this one here. Oh, that's all the top of it. 4 times 10 to the 17th. On the bottom of it, 6,700, let's square that. And squaring that gives us 4.5 times 10 to the 7th power. So now we do, whereas this was multiplying the, so we'll X and figure out how to say best multiplying it. So we multiply the scientific notation there. Here we're going to divide, which means we're going to be 4 over 4.5 and 10 to the 17 over 10 to the 7th, which means you bring that up as minus 7. So we have a 10 to the 10th, and 4 over 4.5 is 0.89 times 10 to the 10th. But you have to move the decimal 1 point this way. And if you move it 1 point that way, then you're going to subtract 1 from there. That means our final answer for this is 8.9 times 10 to the 9th power. But I need to include the units. Newtons. So the force of attraction is 8.9 times 10 to the 9th newtons. Okay, an interesting little problem here. So let's review what happened here with this. Okay. So the first step was identifying the basic formula. The second step was finding what the K is. I guess I'll call that 2A, and then just writing it with that in there is 2B. Then the third step is putting all the different numbers in and making sure they're correctly in there. Multiplying them out is 4. And actually, this is like 4A and for this. And because once you finish multiplying and dividing them, you get the final result, which we call 4B, or you get 5. It doesn't really matter. But just think about those steps that you use to get to it. And the first step in this one, what you need to do is make sure you get the correct equation. So you read carefully this and think about that jointly means multiplying, more multiplying on top where the K is, and inverse means on the bottom. So that's one of the things to remember in this kind of a thing is let's go back to the beginning. Think about for these words, what you have to have your formula include in it, whether you have more multiplying on top or on the bottom, meaning that then you'll divide with it. And in each of these, k is always on the top of the fraction. It's never below on these, because this one you could think of as over 1, and this one you can think of as over 1. So in the fraction, it's always in the numerator. The constant is. So both of these examples hopefully illustrate for you how to get the function, build it in with the right things, do the right calculations in order to get an answer where you also include the units in it. So thank you for watching and listening. I hope this was helpful.